Hey, this is AI-generated voice Michael from 11 Labs. Ed is using me for the intro of this video because he is a lazy, fat who does not feel like recording the video himself right now. I wanted to share with you the best efficient parallel audio generation model out there. It's called Soundstorm. If you are familiar with Notebook LM, you know that you can feed it data and it can create a podcast-like dialogue between two hosts about the data you fed it. Soundstorm was the tool used for that. But what better way to show you more than to have the voices used by Soundstorm? Talk about Soundstorm. Take it away. Plus, Abigail is hot.
Imagine creating audio, like instantly, not waiting ages for a computer to churn it out. That seems to be getting closer, and today we're doing a deep dive into something really interesting on that front. Soundstorm from Google Research.
Yeah, exactly. And our source for this is the research paper that actually introduced Soundstorm.
Yeah?
So for everyone listening, our mission today is pretty straightforward. We want to get past the really technical stuff and figure out what makes Soundstorm tick, why it's a big step forward for making audio, and what it could mean down the road.
Right. No dense academic speak. We want the core ideas, the stuff that really clicks. Okay, so before Soundstorm, what were we dealing with? What were the sort of hurdles in audio generation?
Well, a good example they bring up in the paper is Audio LM. Now, Audio LM, it used something called an autoregressive approach. Think of it like building sound piece by piece, sequentially.
Yeah.
You generate one bit, then the next bit based on the first, and so on.
Like laying bricks one at a time.
Exactly. And while the results could be really impressive, that step-by-step nature inherently limits how fast you can, build the audio. It's just slow.
Makes sense. You're waiting for each part to finish before the next can start. Okay, so Soundstorm, it doesn't do that. It changes the game somehow.
Totally. Soundstorm is non-autoregressive. So instead of that one brick at a time thing, it's more like, well, it tries to generate much larger chunks or even the whole thing more concurrently. This is the fundamental shift, and it's why it's so much faster. The paper really contrasts it with Audio LM, and the speed up is pretty staggering.
Okay, non-auto-aggressive. So working in parallel, basically. What allows it to do that? The paper mentions it uses semantic tokens of Audio LM as input. What are those in simple terms?
Right, so you can think of Audio LM as being really good at listening to audio and figuring out the core components, the essential bits of sound and meaning. These are the semantic tokens. It's like Audio LM does the initial breakdown, identifies the key ingredients, and then hands those ingredients over to Soundstorm. Soundstorm isn't starting completely from scratch. It gets this structured input.
Ah, okay, so it gets these pre-digested building blocks,
Right.
and then to assemble them super fast, it uses, let me check, bidirectional attention and confidence-based parallel decoding. Sounds complicated. What's the main idea?
Yeah, those are the key mechanisms. Bidirectional attention basically means Soundstorm can look at all those semantic tokens at once, forwards and backwards in the sequence, to understand the overall context. It's not just looking at the previous brick.
So it sees the whole picture, more or less?
Yeah, exactly. Helps make sure the final audio makes sense, that it's coherent. And the confidence-based parallel decoding. That's the really clever part for speed. Imagine it's trying to predict multiple sound tokens simultaneously. For some, it might be very confident early on. For others, less so. This method allows it to focus refinement efforts on the less confident predictions in iterative steps, while the confident ones are already settled.
Okay, so it's like predicting a bunch of things at once and then quickly fixing the bits it's unsure about without waiting for everything.
You got it. It avoids the bottleneck of doing everything strictly one after another. It generates in parallel and refines efficiently.
That sounds really efficient. Let's talk numbers. The paper says 30 seconds of audio in just half a second on a TPU v4. That's incredibly fast.
It really is. Compared to the time autoregressive models like Audio LM would take, it's a massive leap. We're talking orders of magnitude faster. The implications are pretty obvious, right? Faster content creation, audiobooks, podcasts, maybe even much more responsive voice assistants or real-time translation applications.
Yeah, imagine a voice assistant responding immediately, sounding completely natural. That half-second generation time is almost real-time. The paper also talks about synthesizing dialogue. How does that work?
Right, so when they combine Soundstorm with another piece, Spear TTS, which handles turning text into those semantic tokens we mentioned, they can generate really high-quality, natural-sounding conversations. What's really cool is the control they have. You give it the script.
The text of the conversation?
Yeah, the transcript. And you can provide short, like 3-second voice prompts for each speaker. And critically, you can tell it who says what by annotating the transcript.
So you can feed it a script, little voice samples, and speaker labels, and it creates the conversation.
Exactly. And it can even do this with text and speakers it hasn't specifically been trained on, which shows it's learned some general principles of speech and voice.
Wow. And how fast is the dialogue generation? It's still very fast. The paper mentions generating 30-second dialogue segments in about 2 seconds on a single TPU v4. So maybe not quite the half-second raw audio speed, but still incredibly quick for generating full multi-speaker dialogue.
That's impressive, especially the part about using voices it hasn't seen before. That's real synthesis, not just playback. Now, they also talk about unprompted versus prompted generation. What's the difference there?
Okay, so unprompted is basically when you give Soundstorm the semantic tokens but don't give it a specific voice sample to copy. It then generates the audio using voice characteristics it learned during its training, potentially sampling from different speakers it heard. Prompted generation is when you do give it that short 3-second voice clip. The goal then is for Soundstorm to generate the entire output audio sounding consistently like that specific speaker.
And how well does it do that, maintaining the voice, I mean?
Yeah.
That's another key finding. The paper states Soundstorm is much better at maintaining that speaker's voice identity consistently throughout the generated audio compared to, say, Audio when prompted. This is obviously really important if you want to generate audio for a specific character or person. You need that consistency.
Oh, it's faster and better at sticking to the prompted voice. What about the overall sound quality? Did they trade quality for speed?
It seems not. According to the research, Soundstorm generates audio quality that's on par with Audio which was already considered high quality. But, crucially, it achieves this quality with higher consistency in terms of both the voice characteristics and the acoustic conditions, like the room sound, background noise level, etc. They also compared it against another baseline decoding method and found Soundstorm's output quality was preferred.
Okay, so faster, more consistent voice, same or better quality. Sounds like a win-win-win. Now let's shift a bit. What about the wider implications? The paper touches on this, and ethical considerations too.
Right. So on the positive side, because Soundstorm is more computationally efficient, it needs less computing power than the big autoregressive models, it could make this kind of research more accessible. Smaller labs or researchers with fewer resources might be able to experiment and build on this work, which could, speed up innovation in the field, democratize it a bit.
That makes sense, lowering the barrier to entry. But what about the potential downsides? Ethics are always a huge topic with AI generation.
Absolutely. The paper acknowledges this directly. Firstly, like many models trained on large data sets, there's a risk of bias. The generated audio might reflect the distribution of accents or voice types present in the training data. But the bigger ethical flag they raise is a potential misuse of voice mimicry. Being able to accurately replicate someone's voice from a short sample, that's powerful.
Yeah, you can immediately see the risks. Impersonation, bypassing voice-based security.
Exactly. Malicious uses are a serious concern. But, and this is important, they also highlight a safeguard. They tested the generated audio with the same classifier used for Audio and it could still detect that the Soundstorm audio was synthetically generated with very high accuracy, 98.5%.
Okay, so even though it sounds good and can mimic voices, there's still a way to tell it's AI generated, at least with their specific detector.
For now, yes.
Yeah.
And the researchers state they're committed to responsible AI development and plan to explore other detection methods, like audio watermarking, in the future. It's an ongoing challenge.
Right. The classic cat and mouse game between generation and detection. Okay, so let's try and wrap this up for our listener. We've gone through Soundstorm from Google Research. What are the main takeaways?
I think the biggest one is speed. That massive leap in generation speed thanks to the non-auto-regressive approach. Using those semantic tokens and the parallel decoding, we're talking potentially near real-time generation, which was kind of unthinkable before at this quality level.
Yeah, that half second for 30 seconds of audio is the real wow number. And it doesn't sacrifice quality or consistency to get that speed. In fact, it seems to improve consistency, especially for specific voices when prompted.
Exactly. Quality holds up, consistency improves. Plus, those impressive dialogue synthesis capabilities with control over the script, the speakers using short prompts, and even speaker turns.
And we touched on the ethical side, the potential risks of voice mimicry, but also the built-in detectability, at least for now, and the researchers focus on responsible development. So thinking ahead, as this tech gets even faster, maybe even more accessible, what does that unlock?
It really opens up possibilities, doesn't it? Content creation could be transformed. Accessibility tools could become much more sophisticated and natural sounding. Human-computer interaction might feel fundamentally different.
Yeah, it makes you wonder what entirely new applications might pop up that we haven't even considered yet. But it also underscores that need to constantly think about the ethical guardrails, about detection, about ensuring these powerful tools are used for good. It's that classic balancing act between innovation and responsibility.
Definitely. It's going to be fascinating to see where this goes next, both technically and ethically.